Hi everybody, welcome to this video on calculating volume using the method of slicing. In this video, we're going to learn how to calculate the volume of a solid using integration and the method of slicing. We're going to explain the theory of the method of slicing and condense that theory into a four-step method. We'll then calculate the volume of a solid in an example problem and solution using integration and the method of slicing. If you're already happy with the theory of the method of slicing and you'd like to see the calculation of the volume of a solid using that method, please use the timestamps in the video description below to skip ahead to that section of the video. For the next section of this video, we're going to explain the theory of the method of slicing. We can use the method of slicing to find the volume of an object, like the one shown below. We graph the object on the x-axis, on the closed interval from A to B. So from x is equal to A to x is equal to b. We define a 2D cross-section of the object at a point x on the x-axis as the region R of x. This 2D cross-section is perpendicular to the x-axis. The cross-section region R of x has an area A of x. If we can find a continuous function a of x that returns the cross-section area as a function of x, so as a function of its position on that x-axis, we can calculate the volume of the solid. The theory of that calculation is explained as follows. We partition the closed interval from A to B into subintervals. Now these subintervals have length delta x. We slice the solid at the partition points with planes perpendicular to the x-axis. Each slice has width delta x, the same length as each subinterval length. We can number the slices from 1 to a number n. So, for example, if we had 5 slices, we'd number them from 1 to 5, and n would be equal to 5. And we'd also number our subintervals from 1 to 5. We can refer to one of the slices as the kth slice and refer to the perpendicular planes bordering it as the plane at x subscript k and the plane at x subscript k minus 1. The kth slice of the solid between the planes x subscript k and x subscript k minus 1 has approximately the same volume as the cylinder between the two planes based on the region R of x. The area of the region R of x is given by the area function A of x. The volume of the cylinder at the kth slice, which we can refer to as V subscript k, can be calculated as V subscript k is equal to the base area of the cylinder multiplied by the height of the cylinder. Now the base area of the cylinder, that's going to be equal to A of x subscript k. And the height of that cylinder, that's going to be equal to our subinterval length delta x. So we can calculate the volume of the cylinder at the kth slice as being equal to the base area by the height of the cylinder, which is equal to A of x subscript k multiplied by delta x. So we have that the volume of the cylinder at the kth slice can be calculated as V subscript k is equal to the base area multiplied by the height, which is equal to A of x subscript k multiplied by delta x. The sum of the volumes of the cylinders approximates the total volume of the solid. So the sum over all of our subinterval lengths, or in other words, the sum over all of our slices of the cylinders at those slices, that approximates the total volume of the solid. Now, we can express the sum of the volumes of the cylinders over those subintervals as being equal to the sum from k is equal to 1 to k is equal to n of V subscript k. And we can express that as being equal to the sum from k is equal to 1 to k is equal to n of A of x subscript k multiplied by delta x. So we have that the sum of the volumes of the cylinders approximates the total volume of the solid, and we can express the sum of the volumes of the cylinders over all of those subintervals, or in other words over all of those slices, as the sum from k equals 1 to n of V subscript k, and we can express that as the sum from k is equal to 1 to k is equal to n of A of x subscript k multiplied by delta x. These terms inside this red rectangle highlighted here, this is a Riemann sum for the area function A of x on the closed interval from A to B. Approximating the total volume of the solid with a Riemann sum is a key step. A Riemann sum of a function on a closed interval is a sum over all of the subintervals of each subinterval length multiplied by a function value from that subinterval. As the subinterval lengths approach 0, the sum of the volumes of the cylinders approaches the actual volume of the solid. As we use more and more subintervals with smaller and smaller subinterval lengths, the sum of the volumes of those cylinders approaches the actual volume of the solid. Or, in other words, as we use more and more slices with smaller and smaller slice thicknesses, the sum of the volumes of the cylinders approaches the actual volume of the solid. As the subinterval lengths approach 0, the value that the sum of the volumes of the cylinders approaches can be equated to being equal to the actual volume of the solid. Now, as the subinterval lengths approach 0, we can express the value of the sum of the volumes of the cylinders using a limit. And that limit is shown below. It's the limit as delta x approaches 0, so the limit as the subinterval lengths approach 0, of the sum from k is equal to 1 to k is equal to n, so the sum over our subintervals of A of x subscript k multiplied by delta x. Now, we can equate the actual volume of the solid as being equal to this limit as the subinterval lengths approach 0 of the sum from k equals 1 to n of a of xk multiplied by delta x. Now, these terms inside this red rectangle highlighted here, this is the limit as the subinterval lengths approach 0 of a Riemann sum of the function a of x subscript k on the closed interval from a to b. Now, this is the definition of the definite integral from a to b of a of x dx. So we can equate the actual volume of the solid as being equal to the definite integral from a to b of a of x dx. If you'd like to learn more about Riemann sums and definite integrals, I do have a video specifically on that topic, which you can click on at the link currently displayed on the screen. For now, for this video, we'll continue to the main definition for the method of slicing. And here's our main definition. The volume of a solid of known integrable cross-section area a of x from x is equal to a to x is equal to b is the integral of the function a from a to b. And our main equation is that our volume v is equal to the integral from a to b of a of x dx. Just to explain that word integrable, our cross-section area function a of x on our closed interval from a to b, that's going to be integrable provided that it's a continuous function from a to b. I do have a video specifically explaining continuous functions if that's something you'd like to learn more about, and I'll quickly say that a quick general description of a continuous function is one which we could draw with a pen on a page with an unbroken line without ever lifting our pen from the page, so with no skips or steps. There are some other finer details too. If you'd like to learn more about those, that video is available. For now, we'll continue discussing the method of slicing. So, having just discussed the theory, now we can condense that theory into a four-step method. Now, very shortly, we're going to demonstrate this four-step method in an example problem and solution. To describe it briefly, in order to calculate the volume of a solid using the method of slicing and integration, we can start first by drawing a diagram of the solid on an axis with a cross-section which is perpendicular to that axis. Next, for our second step, we want to find a formula which describes the cross-section area a as a function of x. For our third step, we want to find the limits of integration that we're going to use. We'll see more about this in our example solution, but essentially we want to look at the extents of our object, the furthest extents of it, along our axis. And our lower and upper limit of integration, they'll coincide to our furthest extents in the positive and negative direction. And then finally, we're going to integrate our function a of x over those limits to calculate the volume. Now, we're going to demonstrate this method very shortly, but first I just want to make one extra point. We aren't limited to cylinder-shaped volumes. To explain the theory, we used a solid volume shaped like a cylinder. which could be approximated with a sum of smaller cylinder volumes. But the method of slicing isn't limited only to solid volumes shaped like cylinders. As long as we can find some continuous function, a of x, that returns the cross-section area of the solid at any point x in the solid, we can calculate its volume. In our next example, we're going to calculate the volume of a solid that does not have a cylindrical shape, using this method of slicing and integration. So here we have our example problem and solution using the method of slicing and integration. We want to calculate the volume of a pyramid. The pyramid is 6 meters high with a square base with each side 3 meters long. And we want to calculate the volume of the pyramid using the method of slicing. So here we're going to use our 4-step method. Our first step is to draw a diagram with a cross-section. We draw the pyramid on its side, with the top of the pyramid at the origin of a graph and the center of the pyramid aligned along the x-axis. We add in the dimensions, the proportions of our pyramid. So our pyramid extends for 6 meters along that x-axis, and at its base, its sides are 3 meters long. We also add in a 2-dimensional cross-section to the object, which is perpendicular to the axis. For our next step, we want to find a function which returns the area of our cross-section as a function of its position on the x-axis. Now, from measurements of our pyramid, the cross-section area of this pyramid at a point x on the x-axis is the area of a square with sides x over 2 meters long. So at the point where x is equal to 6, its sides are 6 divided by 2, it's 3 meters long. At the point where x is equal to 4, its sides are 4 divided by 2, 2 meters long. And at the point where x is equal to 2, its sides are 2 divided by 2, 1 meters long. We can calculate and express the cross-section area A as a function of x to be a of x is equal to one side multiplied by another side, x over 2 squared. And that works out to be x squared over 4. So we have our continuous function describing the cross-section area A as a function of x. Our next step is we want to find the limits of integration. Now, our limits of integration will be equal to the furthest extents of our object along the x-axis. Now, the volume of the pyramid, it extends from x is equal to 0 to x is equal to 6. So our lower limit of integration, a, that's going to be equal to 0. And our upper limit of integration, b, that's going to be equal to 6. So now we have our final step. We want to integrate our function a of x over those limits to find the volume. So to calculate our volume, that's going to be equal to, using our equation, the integral from 0 to 6 of a of x dx. Now our function a of x, and we worked out that that's equal to x squared over 4. So our volume will be equal to the integral from 0 to 6 of x squared over 4 dx. Now we can use our constant multiple rule to take 1 over 4 outside of that integral. So we can calculate the volume V to be equal to 1 over 4 multiplied by the integral from 0 to 6 of x squared dx. Now, still keeping that 1 over 4 separate, we can evaluate that integral to be x cubed over 3 evaluated from 0 to 6. So still keeping that 1 over 4 separate, that x cubed over 3 evaluated from 0 to 6, that's going to be equal to 6 cubed over 3 minus 0 cubed over 3. So that's going to work out to be just 6 cubed over 3, and then we'll need to multiply it by 1 over 4, which we kept separate. So that 6 cubed over 3, that works out to be 216 over 3, and then we need to multiply by that 1 over 4. And when we multiply out those fractions, we get 216 divided by 12, which works out to be 18. So here in this example solution, we've just calculated, using the method of slicing and integration, that the volume of this pyramid is equal to 18 meters cubed. And that's our example solution completed. So to summarize, in this video we've learned how to calculate the volume of a solid using integration and the method of slicing. We've calculated the volume of a solid using the method of slicing in an example problem and solution. In our next video, we're going to learn about the most common application of the method of slicing, calculating the volume of solids of revolution. If you've found this content useful, please subscribe to the channel to receive more content. Thank you very much for your time in watching this video, and see you next video.